Okay, we're back. We're back. We're going to look at some other examples where we can build polynomials of existent, turn some function that has an infinite number of derivatives into an infinitely long polynomial. Dude, amazing. Hopefully you're just like floored right now. You just needed to take a breath after that first video, and now you're back and you're like watching YouTube and you're like, oh my gosh, when is Purvis going to ask me to hit the subscribe button? And when is he going to ask me to hit the notification bell so I don't miss any great new calculus content? When is he going to say that? Not yet. Not yet. Just wait. So what we're going to do now is build another polynomial using the general format of any Taylor polynomial, the nth derivative at c over n factorial multiplied by x minus c raised to the n, that one. All right. We're using a table to do it. So now we're gonna take a function. That function is g of x, which is 1 over x plus 3 squared. Now I'm going to center this at -2. Reason being that when I sub in -2, I'm going to get really nice answers. That's the only reason I'm doing it, is because I'm going to get really nice answers when I sub in -2. You might recognize that subbing in -2 into that original function is going to give me a nice clean 1 raised to a power. So let's go figure out the table here. Okay. So this time I'm asking you for 4 terms. In the first example, I asked you for, I think, a degree. I asked you for a 4th degree polynomial. So again, you are mathematically mature enough to know that terms and degree don't always mean the same thing, right? Terms, okay, there could be 2 terms in a quadratic, but there could be 3 terms in a quadratic. There could be 1 term in a quadratic, right? There just has to be an x squared term to be a quadratic. Number of terms does not, there's no restriction on the number of terms for a nth degree polynomial. Again, I digress. This is asking for 4 terms, so we need to get 4 terms. Whatever degree that is, hey, we'll figure that out. So here we go. So what we're going to do is build it with a table. So our table again is starting with n. We want the nth derivative of the function. We want the nth derivative at -2, the center, and then we want to divide that by n factorial. Remember what we're doing? We're building the coefficients. That's all we're doing. All right, so here we go. At 0 is the original function, x plus 3 to the -2. I wrote it like that because it's going to be wicked easier to take the derivatives. Now, evaluate that at -2, you get 1. Divide that by 0 factorial, you get 1. All right, not so bad. Let's look at the next one. So let's take the first derivative. So -2 chunk to the -3 times the derivative of the chunk, which is just 1. All right, so then we pop in -2. You'll notice that -2 plus 3, that's always going to be 1. So that's going to make 1 to that power super easy. So that's -2. Divide that by 1 factorial, get -2. So 2, no non-zero rows so far. All right, so let's check out the next one, the second derivative now. So power rule time, drop the -3. So 6 chunk to the -4. That chunk turns to 1 when you sub in -2. So evaluating the second derivative at -2, we get 6. And then 6 divided by 2 factorial is 3. Uh-oh, I see a pattern. Is it going to continue? I don't know. Let's find out. So the third derivative now, -4, drop it, multiply it by the 6, little power rule action, -24 chunk to the -5. Well, that's going to be 1, so times -24, divide that by 3 factorial, you get -4. Yeah, that pattern is going to continue, you bet your booty. Well, we got 4 terms here, so let's write those terms out. Remember, these are just the coefficients. This table was just a way to get the coefficient, so we need to tack on an x minus c raised to the n. So c is -2, So we need to use those coefficients. So 1 times x minus negative 2 to the 0, minus 2x minus negative 2 to the first, plus 3 raised to the second, minus 4 raised to the third. And then, of course, you can simplify that down to a much nicer rendition of that, x plus 2. Notice those x plus 2's tell you the polynomial is centered at negative 2. So I'm saying here that the function 1 over x plus 3 squared is approximately these terms. Now, when could I say that it was equal to those terms? Wouldn't I have to have an infinite? I would have to have an infinite number, probably. So you can probably see the pattern there, but let's see if we can notice a few things. What do you notice? Well, it was bouncing back and forth, positive to negative, and it just went up sequentially, right? From 1 to 2 to 3 to 4. So that's really all we've got to do. That coefficient seems like is just going to be 1 greater than the power. So if we start the power at 0 and then go 1, 2, 3, then we'll see if we can figure this out. So negative 1 to the n, that'll start us positive, negative, positive, negative. N plus 1, starting at n equals 0, will start us with 1, then 2, then 3, then 4. And then I've got to have an x plus 2 raised to the n, because that would be raised to the 0, the first, the second, and the third, and so on. So test to make sure that your general, when you come up with a general pattern, make sure that it fits. Don't just figure out a pattern that doesn't work. All right, so let's look at something else. So we've seen to build a polynomial from a function problems, and I'll show you one more before this is all over. But I want to show you a slightly different question that gets to the general form of a Taylor polynomial. So let's say we know a Taylor polynomial already. Right, the idea of the table was to use the function's derivative information to build the polynomial. So mathematics likes to flip it backwards, right? If you can add, you can subtract. If you can multiply, you can divide. You can reverse. The reversibility of mathematics is what makes it so awesome. Well, now I'm going to give you a problem where I have the polynomial. How can I use the polynomial to backtrack and figure out any derivative information about the function? Okay, so this polynomial, I don't know what h of x is, I don't know what the function is, but I know that its Taylor expansion looks like blah, all of that stuff, okay? So, where is it centered? Can y'all figure that out? What is the center of this polynomial? What? Did you say positive 1? Well, then you're right, because, yeah, the center is positive 1. So we're going to use this polynomial to find the fourth derivative of the function h at 1, and we're also going to use it to find the 10th derivative of the function h at 1. Now, let me show you how we can use the general form of the Taylor polynomial. All right. So like I said, we're going backwards. Now, this is what the general term using the function h and the center c. Okay. So if we look at that general form, right, I've replaced f with h, I've replaced c with 1, right, I've done nothing else. So what we see here is that the nth power term is connected to the nth derivative information. Okay, the nth power term is always connected to the nth derivative information. All right, so where are we going to find the fourth derivative of h of x? Well, thinking about this up here, right? Generally speaking, it would be the fourth derivative of h at 1 divided by 4 factorial times x minus 1 to the 4th. Well, goody gumdrops, we have that term. That term was just so happened to be 8 over 7 factorial times x minus 1 to the fourth. They told us what that was. Now what we're doing is we're equating these two terms, right? The fourth derivative at 1 divided by 4 factorial. That coefficient just so happens to be 8 over 7 factorial. Now, that means we can do a little bit of quick algebra. We can set the coefficients equal and simply multiply it by 4 factorial. Booyah, there it is. You can just leave it as that right there. You don't have to simplify, but I did because I'm a nerd. Oh, by the way, hit that subscribe button. It does a lot of help. Hit the notification bell. Make sure you don't miss any great new calculus content. All right. Thanks. Appreciate it, everybody. Let's get the 10th derivative. So where's it going to be? Could I take 10 derivatives? Let's go back up. Could I just take 10 derivatives of this and get the answer? Yeah, but golly, no thank you. So where is the 10th derivative going to live, generally? Well, using the general term of a Taylor polynomial, the 10th derivative information is going to be attached to the 10th degree term. And specifically, it will look like the 10th derivative of h at 1 divided by 10 factorial times x minus 1 to the 10th. All right, that's what it looks like generally. Now, if we recognize the pattern that was given, right? This was the pattern that I gave you for the polynomial. Now, this was a specific pattern. I'm talking the 10th derivative at 1 over 10 factorial. That's generally what happens with all Taylor polynomials. This one, 2 to the n over 2n plus 1 factorial, was the specific pattern. Now, we've got to think about what value of n gets me to the 10th power, x minus 1 to the 10th. Well, clearly that's going to be 9, right? I mean, n plus 1, n has to be 9. So I can use 9 and sub in to the other n's. And I want to be careful about just brainlessly just subbing in n equals 10. I don't want n equals 10. I want the power of x minus 1 to be 10. There's a big difference. It is based on that pattern. It's n plus 1, so n had to be 9. Guard against. It's a bogus thinking alert to just flat out plug in 10 to this problem. We don't want to do that. We want to look for x minus 1 to the 10th. And that means we need n equals 9. So that's what it's going to look like. So when n equals 9, this pattern is 2 to the 9th over 19 factorial times x minus 1 to the 10th. That is the term we're looking for. So we're going to tie together the general term to this specific term, the 10th derivative of h at 1 divided by 10 factorial times x minus 1 to the 10th. That's the general. Boom, the specific is 10 to the 9th over 19 factorial, x minus 1 to the 10th. We can set the coefficients together and do a little bit of simple algebra to get that. The 10th derivative at 1 of h is 2 to the 9th over 19 factorial times 10 factorial. Essentially, think about it this way for a second. What did we do in the table? We took the nth derivative and we divided by n factorial to get the coefficient of x to the n. Well, how do we do that backwards? We're going to take the coefficient and multiply by n factorial to get the derivative information. Hopefully that made sense. Don't ask me to say that again. All right, here we go. One more example. This is the first 4 terms and a general term for f of x is e to the negative 2, and there should be an x sitting right there because e to the negative 2 is a constant. We're not going to make a polynomial for a constant. That should be e to the negative 2x. All right, so again, how do we do it? How do we build a polynomial from a function? We use the table. Here we go. We're going to start at n equals 0. The nth derivative, that's just a function, e to the negative 2x. Let's evaluate that at 0 because it was a Maclaurin polynomial that's centered at 0. Well, e to the 0 is 1. 1 divided by 0 factorial is 1. And then we take a derivative. Derivative of e to the critter is e to the critter, d critter. So that one's negative 2, e to the negative 2x. Evaluate, divide by n factorial. And keep going until you get 4 non-zero. What do I wanted? 4 terms. First 4 terms. So here we go. I can simplify or not. I think not simplifying here might be a little bit easier to see what the pattern is. So I'm going to, here's generally what it looks like. Let's clean it up. Since that center is 0, you just have x, 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 and with the coefficient sitting out front. So those are the first 4 terms. So e to the negative 2x is approximately that polynomial. Remember the picture? It's not exactly matching up. It's close to it. All right, so generally, can we get what the pattern is? Well, again, it alternates. There's powers of 2 in the numerator, and then there's factorials in the denominator. And again, not simplifying 4 over 2 factorial. Everybody was like, it's 2! Well, it's a little bit easier to see what the pattern is sometimes if we leave in those powers of 2 in the factorials. So that's why I chose to do that. And then we come up with a pattern, right? Negative 1 to the n is positive, negative, positive, negative. If I started at n equals 0, I had 2 to the 0, 2 to the first, 2 squared, 2 cubed, so 2 to the n factorial x. So there is the general infinite pattern that I could write like that. All right, so just to recap, in this video, actually the last 2 videos, we've talked about how to use the general term of a Taylor polynomial, which you see here. Ooh, buddy, you better know that one, okay? You gotta know that one. The general term of any Taylor polynomial for any function f at the center value c. That's how we build the polynomial. I'm going to use a table to find those coefficients. I showed you that. I don't need it, but it definitely helps. And remember, the nth derivative is always a